August 15, 1940, RAF Warmwell, Dorset. The Spitfire limped back to base with its port wing smoking and one of its 8 Browning machine guns completely silent. Flight Lieutenant James Ashford brought the fighter down hard on the grass runway, cutting the engine before ground crew could reach him. He was 22 years old, had been flying combat missions for 6 weeks, and had just survived his third encounter with Messerschmitt 109s over the Channel. But survival meant nothing if his aircraft could not fight tomorrow. And tomorrow the Luftwaffe would return with hundreds of bombers attempting to destroy Britain's airfields and break the RAF's resistance. In the dispersal area, 19-year-old Tommy Wheeler knelt beside the damaged Spitfire, examining the jammed gun with hands still stained with bicycle grease from his previous life as a mechanic's apprentice in Bournemouth. The Browning's feed mechanism had shattered, a critical component that channeled ammunition from belt to chamber, essential for the gun to fire. Replacement parts were in London, 2 hours away by truck, assuming the roads were clear and the depot had not been bombed. The squadron needed 12 operational Spitfires by dawn. They had 11. Tommy stared at the broken mechanism, then at his tool bag where, inexplicably, he still carried a bicycle chain from the shop where he had worked 6 months earlier. And he had an idea that violated every regulation in the Air Ministry Technical Manual. Thomas Wheeler was not supposed to be at RAF Warmwell. He was supposed to be in grammar school, preparing for university, following the path his schoolteacher parents had mapped for him toward respectable professional career. But war had scrambled everyone's plans. When the call went out for aircraft mechanics in May 1940, desperate appeal as the RAF expanded frantically to meet German threat, Tommy had volunteered immediately, lying about completing his apprenticeship, exaggerating his mechanical experience. He was accepted because Britain needed bodies more than credentials, because the alternative was letting German bombers fly unopposed. His actual experience was limited but relevant. 3 years working after school at Morrison's bicycle shop in Bournemouth, repairing punctures, adjusting gears, rebuilding wheels. Simple work, repetitive, but it had taught him something valuable about mechanical systems. That function mattered more than form, that improvisation was often superior to following instructions, that understanding how things worked was more important than memorizing what the manual said they should do. The RAF trained him for 6 weeks, barely enough time to learn basic aircraft systems, safety protocols, and which tools not to drop into engine intakes. Then, they shipped him to Warmwell, a grass airfield on Dorset's coast, home to 152 squadron-flying Supermarine Spitfires, the most advanced fighter aircraft in the world, powered by Rolls-Royce Merlin engines producing 1,030 horsepower, armed with 8 303 Browning machine guns capable of firing 1,200 rounds per minute collectively. These machines represented the cutting edge of British engineering, designed by geniuses, built by specialists, maintained according to precise technical specifications. And now Tommy, barely out of adolescence, was responsible for keeping them airborne. The pressure was immense. Every aircraft that could not fly meant one fewer defender against the Luftwaffe formations crossing the Channel daily. Germany had 2,500 bombers and fighters. Britain had perhaps 700 serviceable fighters at any moment. The mathematics of survival were brutal. Lose aircraft faster than factories could build them, and the invasion would come. Every hour a Spitfire sat grounded was an hour Germany gained advantage. The jammed gun on Ashford's aircraft was typical problem. Combat stress revealing weaknesses in systems designed in peacetime. The Browning feed mechanism was elegant but fragile, relying on precisely machined components that could not tolerate the violent vibrations of aerial combat. When parts broke, replacement was only solution. Repair was considered impossible. The tolerances were too tight, the stresses too extreme. But replacement required parts that were not available. So the aircraft would be grounded, the squadron would fly undermanned, and the odds would shift slightly more in Germany's favor, unless someone found another way. Tommy examined the broken feed mechanism with the methodical attention he had learned repairing bicycles. The component was essentially a chain drive, not unlike a bicycle chain, that moved ammunition from the belt into the gun's chamber. The original mechanism used specialized links made from hardened steel, designed specifically for this application, manufactured to precise specifications. 3 of those links had sheared under stress, rendering the entire system inoperative. The bicycle chain in his tool bag was different. Softer steel, larger links, designed for completely different application. It was absurd to even consider it. The stresses in an aircraft gun were orders of magnitude greater than anything a bicycle experienced. The vibrations alone would probably shake a bicycle chain apart in seconds. And even if it somehow held together, the tolerances were wrong. The chain might not mesh properly with the sprockets, might jam, might cause catastrophic failure that could endanger the pilot. But Tommy had spent 3 years watching how different chains performed under stress. He understood that official specifications were often conservative, that manufacturers built in safety margins, that real-world performance sometimes exceeded theoretical limits. He also understood desperation, that Britain was losing aircraft faster than it could replace them, that every operational fighter mattered, that following regulations perfectly while losing the war was pointless. He found squadron leader David Henderson in the operations room, studying maps of German bomber formations. Henderson was 31, veteran of Spain's Civil War, exhausted from flying 3 missions daily. Tommy explained the problem and his proposed solution. Henderson looked at him like he was insane. "You want to repair a Browning gun with a bicycle chain? Have you lost your mind? Those guns operate under extreme stress. If your improvised repair fails during combat, Ashford could be defenseless against a Messerschmitt." Tommy stood his ground. "If I don't try, he's definitely defenseless. 1 gun down means 12.5% less firepower. If I try and it works, he's fully operational. If I try and it fails, we're no worse off than we are now." Henderson considered this logic. It was sound if you accepted the premise that official protocols could be ignored. "Fine, try it. But test it thoroughly on the ground before I let Ashford take it up. If it fails testing, we ground the aircraft until proper parts arrive. Clear?" Tommy nodded and got to work. He had perhaps 4 hours until dawn, when the squadron would scramble to meet the day's first German raid. 4 hours to accomplish something the Air Ministry's engineers would say was impossible. The first challenge was sizing. The bicycle chain links were larger than the Browning's original feed mechanism. Tommy needed to modify the sprockets to accommodate the different pitch, the distance between links. He used a file to carefully reshape the sprocket teeth, working by the light of a single lamp while other ground crew slept in exhausted shifts around him. The work required precision. Too much material removed and the sprockets would be weakened. Too little and the chain would not mesh properly. He tested the fit repeatedly, placing chain over sprocket, checking for smooth movement, adjusting, testing again. The bicycle chain was roller chain, similar in principle to the gun's original mechanism but cruder, less refined. It should not work. But should not and would not were different things, and Tommy had learned that mechanical systems often performed beyond their specifications if you understood their actual capabilities, rather than their theoretical limits. After 2 hours, he had the fit correct. The chain meshed with the modified sprocket smoothly, though not as perfectly as the original mechanism. There was more play, more tolerance, more potential for vibration, but it moved, which meant it could potentially function. He installed the modified mechanism into the gun, reconnecting the ammunition belt, checking alignment, ensuring nothing would jam when the gun fired. The other armorer, a Scotsman named McGregor who had 15 years' experience with military weapons, watched with mixture of fascination and horror. "Laddie, you're either a genius or you're about to kill someone. I can't decide which." Tommy kept working. "Neither can I, but we'll find out soon enough." The test would be critical. They would load the gun with blank ammunition, no projectiles, just powder to generate firing pressure, and test whether the mechanism could withstand the violent cycling that occurred when the gun fired. If the bicycle chain held together through a burst of sustained fire, it might work in combat. If it failed, at least it would fail safely on the ground, rather than at 20,000 feet with Messerschmitts closing in. At 3 a.m., they wheeled the Spitfire to the far end of the airfield, away from sleeping personnel and fuel stores. Tommy loaded a belt of blank rounds, secured the gun, and stepped back. McGregor, standing at safe distance, would trigger the gun electrically while Tommy observed the mechanism through an inspection port. If anything went wrong, if the chain shattered, if fragments flew, if the gun jammed catastrophically, they needed to see it happen to understand what failed. McGregor called out, "Ready?" Tommy took a breath. "Fire!" The gun hammered out 15 rounds before Tommy signaled McGregor to stop. The sound was normal, the distinctive bark of a Browning 303 that every ground crew member knew intimately. Tommy examined the mechanism with a flashlight, hands shaking slightly from adrenaline. The bicycle chain was intact, scarred, stressed, showing wear, but intact. The modified sprockets showed no signs of failure. The alignment was holding. Again, Tommy said. Longer bursts this time. McGregor fired 30 rounds, then 50, then a full sustained burst of 100 rounds. Approximately 8 seconds of continuous fire, about what a pilot would use in a typical engagement. The gun continued to function. The bicycle chain, designed to move a person peacefully through streets and countryside, was now channeling ammunition at rates that would have seemed impossible to its manufacturer. But functioning under blank fire was different from functioning with live ammunition. The actual projectiles added mass, added recoil stress, added complications that blanks could not replicate. The only way to know if the repair would work in combat was to try it in combat. Tommy reported to Squadron Leader Henderson at 4:30 a.m. The gun is functional. I've test-fired 200 rounds. The improvised mechanism is holding, but I cannot guarantee it will work under combat conditions. Henderson studied the young mechanic. Can you guarantee anything in this war? Tommy shook his head. Henderson continued. Neither can I. I cannot guarantee my pilots will come back. Cannot guarantee the airfield won't be bombed. Cannot guarantee we'll win. All I can do is make sure we have maximum number of operational aircraft when the Germans arrive. You've given me one more Spitfire than I had yesterday. That's all anyone can ask. He paused. But I want you in the cockpit when Ashford tests it. If something fails, you need to see it, understand it, learn from it. If we're going to start improvising repairs, we need to know what works and what kills people. At 5:30 a.m., as dawn broke over the channel, Flight Lieutenant Ashford climbed into his Spitfire with Tommy strapped into the narrow space behind the pilot's seat, a position normally used for training flights, cramped and uncomfortable, but offering view of the gun mechanisms. They would fly a test mission, climb to 15,000 feet, fire the guns at sea target, verify the repair held under actual combat conditions minus the combat. The Merlin engine roared to life. The Spitfire rolled forward, and Tommy Wheeler, bicycle mechanic turned aircraft armorer, prepared to discover whether his improvisation was genius or fatal error. The flight was terrifying and exhilarating simultaneously. Tommy had never flown before, never experienced the sensation of Earth dropping away, of forces pressing against his body during turns, of seeing England spread below like a map rendered in green and brown. But he had no time to appreciate the experience. He was focused entirely on the gun mechanisms, watching through inspection ports as Ashford put the Spitfire through maneuvers, rolls, dives, tight turns that generated forces several times gravity. At 15,000 feet, Ashford leveled out over the channel and radioed back. Ready to test? Tommy gave thumbs up, the only communication possible over the engine noise. Ashford squeezed the trigger on his control column. 8 guns fired simultaneously, 7 with their original mechanisms, 1 with Tommy's bicycle chain improvisation. The aircraft shuddered as 1,200 rounds per minute tore through the air, tracers arcing toward the empty sea below. Tommy watched the modified mechanism through the inspection port. The bicycle chain was moving, flexing, stretching, absorbing stresses it was never designed for, but it was holding. The rounds were feeding smoothly. The gun was firing. He signaled Ashford to cease fire, examined the mechanism more closely. Wear was evident. The chain was stretching. The links were showing stress, but no catastrophic failure, no jamming, no fragmentation that could damage other systems. Ashford fired 2 more bursts, longer duration, sustained pressure. The gun continued to function. Whatever Tommy had created, it worked. Not perfectly, not elegantly, not according to any official specification, but it worked. The Spitfire had 8 operational guns instead of 7, and in the calculus of aerial combat where every advantage mattered, that extra gun could mean the difference between downing a bomber or letting it through to drop its payload on cities, airfields, factories. They returned to Warmwell at 6:45 a.m. Ground crew swarmed the aircraft, refueling, rearming, preparing for the day's operations. Tommy disassembled the modified gun, examined every component, documented what he found. The bicycle chain had survived approximately 500 rounds, far less than the original mechanism's rated capacity of 10,000 rounds, but sufficient for several combat engagements. It would need replacement more frequently, would require more maintenance, would demand closer monitoring, but it would keep the aircraft operational when proper parts were unavailable. Squadron Leader Henderson reviewed Tommy's report and made decision. Implement this repair on any aircraft with damaged feed mechanisms. Document the procedure. Train the other armorers. We're going to need every gun we can keep firing. The improvisation was becoming doctrine. Desperation was becoming innovation. Word spread quickly through RAF stations in southern England. The bicycle chain repair was radical departure from official protocols, but it worked. And in August 1940, working was the only metric that mattered. Other squadrons requested technical details. Tommy wrote instructions, drew diagrams, explained the modifications required. Within 2 weeks, a dozen Spitfires and Hurricanes were flying with improvised feed mechanisms, each representing aircraft that would otherwise be grounded awaiting replacement parts. But the Air Ministry was not pleased. Technical officers in London, far from combat, issued directive. Unauthorized modifications to aircraft weapon systems were strictly forbidden. Violations would result in court-martial. All improvised repairs must be removed immediately and replaced with proper components. Squadron Leader Henderson received this directive, read it carefully, then filed it in the lowest drawer of his desk and continued operating his squadron as if it did not exist. He was not alone. Across Fighter Command, squadron leaders made similar calculation. They could follow regulations and lose the battle, or they could ignore regulations and have fighting chance. Most chose fighting chance. The system that had designed the Spitfire and the Browning gun was same system that could not deliver replacement parts fast enough, that prioritized paperwork over pragmatism, that valued proper procedure over actual results. Tommy became minor celebrity among ground crews, the young mechanic who had broken the rules and saved aircraft. Other armorers began consulting him about improvised repairs, using car parts to replace damaged hydraulic systems, fabricating new components from scrap metal, jury-rigging solutions that officially should not work but actually did. Tommy's answer was always the same. Try it. Test it. If it works and doesn't kill anyone, use it. This attitude was revolutionary in military context, where hierarchy and procedure were designed to prevent chaos. But war was already chaos, and procedure that could not adapt to reality was liability rather than asset. Tommy represented bottom-up innovation, solving problems not through official channels but through practical experimentation, not through following manuals but through understanding principles. On August 30th, 1940, Ashford's Spitfire encountered a formation of Heinkel 111 bombers escorted by Messerschmitt 109s over Southampton. The engagement lasted 4 minutes, an eternity in aerial combat, where most encounters ended in seconds. Ashford fired multiple bursts from all 8 guns, including the one repaired with bicycle chain. He claimed 1 bomber damaged, 1 fighter probably destroyed. The bicycle chain mechanism functioned throughout the engagement without failure. When he landed, Ashford sought out Tommy. "Your repair saved my life today. That extra gun let me maintain fire when I needed it most. Thank you." The Battle of Britain reached its climax in September 1940. The Luftwaffe launched massive daylight raids, hundreds of bombers and fighters attempting to destroy RAF airfields and break British will to resist. Fighter Command flew to exhaustion, pilots completing 4 or 5 missions daily, ground crews working 18-hour shifts to keep aircraft operational. Every plane mattered. Every gun mattered. Tommy's improvised repairs were keeping aircraft in service that would otherwise be grounded. But the bicycle chain solution had limitations. The chains wore out quickly under combat stress. Tommy established replacement schedule. After every 500 rounds, the chain had to be inspected and usually replaced. This created new problem. Bicycle chains were not military equipment, were not stocked by supply depots. Tommy had to source them from civilian bicycle shops, requisitioning them through unofficial channels, building network of suppliers who probably violated rationing regulations by providing chains for military purposes they were not officially supporting. He visited shops in Bournemouth, Dorchester, Weymouth, anywhere within cycling distance of Warmwell. He explained to shop owners what he needed and why. Their bicycle chains were keeping Spitfires flying, keeping pilots alive, keeping Britain in the fight. Most owners donated chains without payment. Some kept boxes ready for Tommy to collect. A few shop owners began modifying chains specifically for his needs, reinforcing links, adjusting dimensions, creating specialized components from civilian materials. This grassroots supply network represented something the Air Ministry had not anticipated: civil-military cooperation at local level, bypassing official logistics entirely. It was inefficient by bureaucratic standards. No paperwork, no accounting, no oversight. But it was effective. which mattered more than efficiency when the alternative was losing the war. On September 15th, the day that would later be commemorated as Battle of Britain Day, Fighter Command flew more than 1,000 sorties, shooting down dozens of German aircraft and forcing the Luftwaffe to recognize that Britain's air defenses were not broken. Tommy worked through that entire day, maintaining guns, replacing bicycle chain mechanisms, keeping aircraft operational. 12 Spitfires from a 152 squadron flew multiple missions. 8 of them had Tommy's improvised repairs. All returned safely. That evening, exhausted, sitting with other ground crew members drinking tea and smoking cigarettes they had been hoarding, Tommy reflected on what they had accomplished. He was 19 years old, had no formal engineering education, had improvised a repair that violated every official regulation, and it had worked. Not because regulations were worthless. Regulations existed for good reasons, but because reality demanded flexibility, because survival required creativity, because there was difference between doing things right and doing right things. McGregor, the Scottish armourer, raised his tea mug. To bicycle chains, may they keep our lads flying until proper parts arrive. Everyone drank to that. October brought change. The Luftwaffe shifted strategy from daylight raids to nighttime bombing. The Blitz. Fighter Command's immediate crisis eased slightly. Supply lines caught up with demand. Replacement parts became available. The bicycle chain repairs were gradually replaced with proper Browning mechanisms as official components arrived from factories and depots. Tommy expected his improvisation to be forgotten, dismissed as desperate measure that was no longer necessary, but something unexpected happened. The Air Ministry sent investigators to Warmwell, not to court-martial anyone but to study what had been done. They interviewed Tommy, examined his documentation, tested the improvised mechanisms. Then they did something remarkable. They incorporated his approach into official guidance. The new technical bulletin, distributed to all RAF maintenance units, acknowledged that field improvisation may be necessary when proper replacement parts are unavailable, and provided guidelines for acceptable temporary repairs using non-standard components. It did not specifically mention bicycle chains. Bureaucracy had limits, but it legitimized the principle that Tommy had demonstrated, that mechanics on the ground, facing real problems with real consequences, could be trusted to find solutions, even if those solutions deviated from approved procedures. This represented quiet revolution in military thinking. Traditionally, armies valued standardization and compliance, everyone doing the same thing the same way, following same procedures, using same parts. This approach had advantages: predictability, reliability, ease of training and supply. But it had disadvantage of inflexibility. When standard procedures failed or standard parts were unavailable, the system locked up, unable to adapt. Tommy's improvisation proved that flexibility could coexist with discipline, that innovation could emerge from necessity, that expertise resided not just in engineering offices, but also in hands of mechanics who understood how things actually worked, rather than how manuals said they should work. This lesson would influence British military doctrine for remainder of the war, encouraging field innovation, reducing rigid adherence to specifications, trusting frontline personnel to solve problems creatively. For Tommy personally, recognition brought unexpected consequences. He was promoted to sergeant, given responsibility for training new armorers, asked to develop curriculum teaching improvised repair techniques. He was also offered opportunity to attend engineering school, accelerated program for promising technicians, paid by the military, designed to convert practical experience into formal qualification. He accepted, though it meant leaving Warmwell. His last day at the base, Flight Lieutenant Ashford presented him with gift, a section of bicycle chain, mounted on a wooden plaque, engraved with, "The Chain That Saved the Sky, August 1940. It was recognition that mattered more than any official commendation. Acknowledgement from the pilot whose life had depended on Tommy's willingness to try something impossible. Tommy attended engineering school from January to June 1941, studying mechanical engineering, materials science, and aircraft systems. The education formalized what he had learned intuitively through bicycle repair and wartime improvisation. He discovered that his instincts had been correct, that bicycle chain could withstand stresses far beyond its rated capacity if used properly, that safety margins in engineering specifications were often conservative, that understanding principles mattered more than memorizing specifications. But he also learned the limitations of improvisation. His instructors explained why proper parts were designed as they were, why specifications existed, why deviating from standards could be dangerous. Your bicycle chain repair worked, one professor told him, because you understood the forces involved and adapted accordingly. But someone less knowledgeable attempting the same repair could have caused catastrophic failure. Innovation requires understanding. Improvisation without knowledge is just gambling. Tommy absorbed this lesson. When he returned to active service in July 1941, assigned to RAF Maintenance Training Command, he taught both improvisation and caution. His curriculum included standard procedures and approved repairs, but also section on field improvisation, teaching mechanics how to evaluate whether non-standard repairs were safe, how to test improvised solutions, how to know when to take risks, and when to follow regulations. The war continued. Tommy never returned to combat operations but contributed to the war effort through training hundreds of mechanics who maintained aircraft across all theaters: Europe, North Africa, Asia. Some of his students later wrote to him, describing how the improvisation techniques he taught had kept aircraft operational in desperate circumstances. Hurricane fighters in Burma, repaired with parts from crashed Japanese aircraft, bomber hydraulic systems jury-rigged using plumbing components from destroyed buildings, engine parts fabricated from scrap metal when supply lines failed. Each story reinforced the lesson that war demanded flexibility, that survival required creativity, that sometimes the best solution was not the proper solution but the available solution. But each story also carried warning. Improvisation had costs. Some improvised repairs failed, sometimes catastrophically. Some aircraft were lost because mechanics attempted repairs beyond their capability. The line between heroic innovation and reckless endangerment was thinner than anyone wanted to admit. Tommy wrestled with this moral complexity. He had saved aircraft and potentially lives through his bicycle chain repair. But had he also encouraged culture of risk-taking that got people killed? Was he hero, or was he person who had normalized violations of safety protocols? The answer, he concluded, was both. War was morally ambiguous. Every decision involved trade-offs. The best you could do was make informed choices and accept consequences. The war ended in 1945. Tommy, now 24, returned to civilian life with engineering degree, military experience, and reputation as innovator. He was recruited by Hawker Aircraft Company, manufacturer of the Hurricane fighter, to work in their design department, specifically in division focused on maintainability and field repair. His job was to design aircraft that could be maintained by mechanics like he had been, young, minimally trained, working in difficult conditions with limited resources. This work was revolutionary. Traditional aircraft design prioritized performance, speed, altitude, armament. Maintainability was secondary consideration, but Tommy's experience had taught him that aircraft that could not be maintained in field were useless, regardless of their theoretical performance. He pushed for designs that used standard components, that allowed repairs without specialized tools, that anticipated field improvisation, rather than treating it as deviation from proper procedure. His influence can be seen in post-war British aircraft designs: more modular construction, easier access to critical components, greater tolerance for non-standard repairs. These features made British aircraft popular with smaller air forces that lacked sophisticated maintenance infrastructure. Exactly the kind of pragmatic innovation that Tommy had pioneered with his bicycle chain repair. He married in 1947, a woman named Patricia who had worked as radio operator during the war, who understood military culture and wartime improvisation. They had 3 children. Tommy's career prospered. He eventually became chief engineer at Hawker, leading design teams, mentoring younger engineers, always emphasizing that good design required understanding how things would be used in reality, not just how they should work in theory. But he remained modest about his wartime contribution. When asked about the bicycle chain repair, he always downplayed it. "I was 19 years old, desperate, and willing to try something that probably should not have worked. I was lucky it did. The real heroes were the pilots who flew with my improvised repairs, trusting their lives to my inexperience." He refused to take sole credit, always emphasizing that innovation was collective effort, that his idea only worked because squadron leaders were willing to take risks, because pilots were willing to fly with improvised equipment, because bicycle shop owners were willing to donate chains because the system was flexible enough to allow bottom-up innovation. In 1965, 25 years after the Battle of Britain, the RAF invited him to commemoration ceremony. He attended, now 44 years old, successful engineer, father of 3. He met elderly veterans who had flown Spitfires and Hurricanes during the battle. Several remembered him, remembered the young mechanic who kept their guns firing when parts were unavailable. Flight Lieutenant James Ashford, now retired Air Vice Marshal, gave speech at the commemoration. He described the battle from pilots' perspective, the fear, the exhaustion, the knowledge that Britain's survival depended on handful of fighters and handful of pilots. Then he told story that most attendees had never heard, about the young mechanic who repaired a Browning gun with bicycle chain, who kept aircraft operational when official supply system failed, who represented thousands of ground crew members whose names never appeared in history books, but whose work made victory possible. "We pilots got the glory," Ashford said. "Our names are remembered. We received medals and recognition, but we could not have flown without the ground crews who kept our aircraft operational, who worked 18-hour shifts, who improvised solutions when proper solutions were unavailable." Thomas Wheeler was one of those men. His innovation, using bicycle chain to repair a gun mechanism, seemed small, even comical, but it represented something larger, the willingness to think creatively under pressure, to break rules when following rules meant failure, to take responsibility for finding solutions rather than waiting for someone else to provide them. Ashford continued, "That attitude, that combination of creativity, responsibility, and pragmatism is what won the Battle of Britain, not just superior aircraft or brave pilots, but an entire system of people who refused to accept defeat, who found ways to keep fighting even when everything seemed impossible." Tommy Wheeler, with his bicycle chain, embodied that spirit. He was 19 years old, had no formal engineering education, had no authority to modify aircraft weapon systems, but he had the courage to try something new, the skill to make it work, and the integrity to test it thoroughly before risking a pilot's life. That's heroism as important as anything that happened in the air. The audience applauded. Tommy sat embarrassed, uncomfortable with attention. After the ceremony, several young engineers approached him, asking about his wartime experiences, wanting to know how he had thought of using bicycle chain, how he had known it would work. Tommy answered honestly, "I didn't know it would work. I just knew that doing nothing was unacceptable. So I tried something, tested it carefully, and got lucky." That's not engineering genius, that's just refusing to give up. But it was more than that. It was demonstration that expertise came in many forms, that formal education was valuable, but not sufficient, that solving real problems required practical knowledge combined with willingness to take calculated risks. Tommy's bicycle chain repair was not just mechanical fix. It was proof that innovation could come from anywhere, from anyone willing to think creatively and act courageously. The true climax of Tommy Wheeler's story was not the moment he installed the bicycle chain, nor the successful test flight, nor even the combat mission where the improvised repair functioned perfectly. The climax came decades later, in a conversation that revealed the full significance of what he had done. In 1988, Tommy was invited to speak at Royal Aeronautical Society about field maintenance during wartime. He was 67, retired, suffering from arthritis that made working with tools painful. He prepared modest presentation about improvised repairs, illustrated with photographs and technical drawings from his wartime notes. He expected audience of perhaps 30 engineers interested in historical curiosities. Instead, the lecture hall held more than 200 people, engineers, historians, military officers, veterans. During question period, a young woman stood. She identified herself as Dr. Sarah Mitchell, aerospace engineer working on next-generation fighter aircraft. "Mr. Wheeler, your bicycle chain repair has been studied in every engineering course I've taken. It's used as case study in design flexibility, in materials science, in systems engineering. But I want to know something the textbooks don't explain. How did you have the courage to try something that everyone said was impossible? How did you trust your judgment over all the experts who designed the original system?" Tommy thought carefully before answering. "I didn't trust my judgment over the experts. I trusted that the experts who designed the Browning gun had built-in safety margins, had made it stronger than minimally necessary. I was betting on their competence, not dismissing it. And I understood that specifications are answers to specific questions. The question the designers answered was, what components will function reliably for 10,000 rounds under normal conditions? But the question I needed to answer was different. What components will function adequately for 500 rounds under emergency conditions? Different question, different answer. He paused, gathering thoughts. The courage came from understanding that the greatest risk was doing nothing. If I did nothing, the aircraft was definitely grounded. If I tried something and it failed on the ground during testing, the aircraft was still grounded, no worse than before. If I tried something and it worked, we gained operational capability. The risk-reward calculation made trying worthwhile. That's not courage. That's just basic logic applied to desperate circumstances. But it was courage. Courage to trust his understanding of mechanical principles over official procedures. Courage to take responsibility for consequences if his improvisation failed. Courage to act when inaction was safer, bureaucratically, but morally unacceptable. That courage, repeated thousands of times by thousands of people during the war, was what made victory possible. Thomas Wheeler died in 1995 at age 74 of pneumonia. His obituary in the Times mentioned his career at Hawker Aircraft, his contributions to post-war aviation design, and briefly noted his wartime service. It did not mention the bicycle chain repair. By then, it was footnote in history, overshadowed by more dramatic stories of aerial combat and heroic sacrifice. But in engineering schools across Britain and beyond, the story persisted. The bicycle chain repair became legendary example taught to students as illustration of principles that transcended its specific circumstances, that understanding fundamentals mattered more than memorizing specifications, that improvisation required knowledge, not just creativity, that good engineering meant designing systems that could be maintained in imperfect conditions by imperfect people. Tommy's papers, donated to the RAF Museum after his death, revealed something unexpected. He had kept meticulous records of every improvised repair he performed or supervised during the war. Hundreds of cases, documented with technical drawings, test results, success rates, and failure analysis. This documentation became valuable historical resource, helping historians understand how military logistics actually functioned during wartime, not through official supply chains and proper procedures, but through improvisation, informal networks, and creative problem-solving by people whose names never appeared in official records. His 3 children, all pursued careers in engineering or science, established scholarship in his name at the engineering school he attended. The scholarship is awarded annually to students who demonstrate practical problem-solving ability combined with theoretical understanding, the combination Tommy embodied. The scholarship essay question asks applicants to describe how they would solve a technical problem with limited resources, encouraging the same creative thinking that led to the bicycle chain repair. In 2015, 75 years after the Battle of Britain, the RAF unveiled small memorial at former RAF Warmwell site. Most of the airfield has returned to farmland, but a small museum preserves its history. The memorial includes a bronze sculpture, a Spitfire's wing section with a Browning gun, and beneath it, a bicycle chain. The plaque reads, "In memory of the ground crews who kept the fighters flying. Their names are forgotten, but their ingenuity saved Britain." Tommy Wheeler would have appreciated that memorial, not because it honored him specifically, he always resisted personal recognition, but because it acknowledged that war was won, not just by heroes in the air, but by ordinary people on the ground, who refused to accept that problems were unsolvable, who trusted their judgment when circumstances demanded it, who understood that following regulations perfectly while losing was less important than bending regulations thoughtfully while winning. War changes men, nations, and truths. A teenage mechanic used a bicycle chain to repair a Spitfire gun. In doing so, he proved that innovation comes not just from laboratories and design offices, but from anyone willing to think creatively under pressure. If this story made you reflect on ingenuity, adaptability, and the importance of practical problem-solving, share it. Because the greatest innovations often come not from following rules, but from understanding principles deeply enough to know when rules can be safely broken. And sometimes the most important contributions to history are made by 19-year-olds with bicycle chains and the courage to try something impossible.